Thank you.
Sometimes I have, let's say, a complicated function that I want to find its Laplace transform. So what I do is I can use these properties to make things easier. So linearity might be an obvious property for now, but if you look at the next properties, you will see that these are not obvious to see. So, and they can be very powerful. For example, what if I have g of t plus some constant k? If I know the Laplace transform of g of s, can I get the Laplace transform for this guy easily without having to do the integral for that function with this shift factor? This is an example of a property that we will see. What if I know the Laplace transform? What if I want to Laplace transform of the derivative of g prime? Can I get that easily? What if I want to know the Laplace transform of the integral of g? So using the properties, just by the knowledge of the Laplace transform of g, I can get the Laplace transform of its derivative, its integral, its shifted version, and a lot of varieties. So these are reasons to why we care about studying some Laplace transform properties. So the next property we want to study is multiplication by the exponential. So the Laplace transform of f multiplied by an exponent is capital F s plus a. So an exponent in the time domain is equivalent to a shift in the frequency domain. And if we want to show that, so what is this? So what is the Laplace transform of f e to the power minus at? It's simply the integral of f e to the power of minus at e to the power of minus st dt, which is equal to the integral of f e to the power of minus a plus s t dt, which is equal to capital F s plus a. Why? Because according to the Laplace transform, according to the Laplace transform definition, whatever I have applied by t here, it was s. So then with that we have capital F of s. So if I change that variable, then the argument of the function capital F needs to change accordingly. Is that clear? Do you have any questions about this part? Okay. So if I erase my derivation, we get the following. Exactly what we just did. So if I have, let's say, an exponent, so this tells me something, that the Laplace transform of the exponential function is simply 1 over SA. Why? Because the Laplace transform of the unit step is 1 over S, so which is equal to 1. The unit step is equal to 1, right? So which means that the Laplace transform of the exponential, you can think about it as a unit step multiplied by the exponential, which gives you 1 over S plus A. So here are some examples on using this property. Again, what I just mentioned is that, so the Laplace transform of the unit step is 1 over S, we have S plus A. The Laplace transform of t, if you remember, it was 1 over S squared. It was the ramp input. Let me remind you about it. It was this guy. It was 1 over S squared, which means that the Laplace transform of t e to the power of minus at is simply one over S plus A all squared. Similarly, the Laplace transform of the sine function was omega over s squared plus omega squared. So if we multiply it by an exponent, then we have s plus a here. Similarly, for the cosine function, which was s over s squared plus omega squared, so we have s plus a over s plus a squared plus omega squared. Any questions so far? All right, we have another important property. So the multiplication by time in the time domain corresponds to minus the derivative of capital F. Okay, so let's verify this for a simple example. So we said that the Laplace transform of 1 is 1 over s, right? Now the Laplace transform of t is simply using this property. So this is 1 multiplied by t is minus the derivative of this guy, 1 over s, using the property, right? And that gives me 1 over s squared. Now, if I go back to my ramp example, using the definition, it was 1 over s squared. So you see that using this property, we can easily compute this Laplace transform without using the definition. Now I can apply this again and find the Laplace transform of t squared, which will be simply minus the derivative of this guy, 1 over s squared. Right? I think it's minus 1 over s cubed. So the idea here is that you use this property, multiplication by time, and it corresponds to a derivative in the frequency domain. So let's see the derivation for this. So this is the Laplace for u of s. Now the Laplace of tu is 1 over s squared. Now I was wrong in my calculation. The Laplace of this guy is simply 2s cubed, and etc. So with that, we can have this formula. The Laplace transform of t to the power of n, multiplied by the unit step, is simply n factorial over s to the power of n plus 1. The next property is that the Laplace transform of the derivatives. So if I have a function f, the Laplace transform of its derivative is sf minus f0, evaluated as 0, at 0. Then the Laplace transform of the second derivative is s squared f minus s multiplied by the evaluation of this function at 0 minus f prime as 0. So if I have 0 initial conditions on everything, so this is 0, 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 this is 0. So every derivative corresponds to multiplication by s here. So previously it was multiplication by time, and the time domain corresponds to minus the derivative of capital F. Now it's kind of the opposite direction. If you have the derivative of f, you multiply by s in for the transformed version of the function. Is this part clear? Any questions? I'll pause here for a minute in case you have any questions. Okay. So I will give you this exercise and I'll give you 5 minutes. Apply the Laplace transform to the ODE. I want you to give me what is capital X of S. So we said we have some properties. One of the properties is the finding the Laplace transform of the derivative and the second derivative. Okay, you don't know the function X now, okay? You don't know it. So you have a differential equation. So usually what you want to do is you want to, instead of finding X using the differential equation kind of analysis, you can use the Laplace transform with these easy properties so that you can get capital X as a fraction. And once you're done with that, when later after we learn the inverse Laplace transform, you will find what is X of t. So now what we have is the following. We have a differential equation, apply the Laplace transform to it, in order to get the expression for this capital X of S in the frequency domain. These are the two formulas that you will need. So what you do is you apply the Laplace transform to both sides and assume that t is greater than or equal to 0. Okay? Can you guys do it? All right. So I'll give you 5 minutes to figure it out. I'll set a timer just right now. Do you guys need more time, or have you figured it out? Okay, you got it. 2 minutes it is. How about now? You got it? You feel stuck? Or you got a solution? Or you haven't tried at all? Come on, we have 31 students. Stuck. Okay, so what was the difficulty? What did you try? After applying the first step, what happened?
Doctor,
Yes.
after finding the first step, I couldn't combine it all together.
Okay. So let's go through it together. Okay. How about that? See, so what you do is really simple algebraic manipulations. Nothing is complicated. It's maybe because it's the first time you see it, you get stuck. So let's apply this to this guy, and then we apply this to this guy, and just see what happens. So I want to find the Laplace transform of the left-hand side. So what I get is s square x of s minus s x of 0, which is 4, minus x prime 0, which is 5, plus 3. This is sx, sorry, this is sx, s capital X of s. This is, so I'm finding the Laplace transform of x prime, minus x0, which is 4, plus, what is the Laplace transform of this? It is 2 capital X of s. This is all equal to, what is the Laplace transform of 1? It's 1 over s. Any questions about this step? Please stop me at any time. Just say your question, interrupt me. Okay. Now we're done with this step. We just applied the Laplace. So notice the following. In the previous examples, I gave you a function and asked you to find the Laplace transform. Here, because we have a differential equation, we actually do not know the function. We're trying to find the function. So the Laplace transform and its properties can help us identify that function. And in order to do that, we find the Laplace transform, find the expression of capital X, and then later on, once we do the inverse Laplace transform, we can get the solution to the differential equation. Okay, so from here, how do I proceed? We have x of s, so take it as a common factor, multiplied by what? Let me use red here, multiplied by s squared plus 3s plus 2, right? This is equal to what? 1 over s. Now let me take all the other sides here to the right. 1 over s plus 4s plus 5 plus 12, right? This gives me x of s being equal to what? This guy divided by this guy. And we have it as a fraction. And that's pretty much it. Then with the this Laplace transform, we will see that we can easily find the solution to it. Any questions about this example? Are you guys sure that you understand this example? Because it's very important. Okay.
Clear, but we need another one example to try.
Okay. How about this? I'll give you a. This is easy. ما طلبت شيء. Let's change it. I can change it now for you to try on your own. Okay, forget about this guy. Make it 0. Let's make this guy 0, just for simplicity. Okay. Make this 3. Do that. I'll give you 3 minutes to try it on your own.
Okay.
Yeah, the right-hand side of the first of the differential equation is 3. Yes. Any success? You guys got it?
I finished, but I don't know if it's correct or not.
What do you have?
3 over s plus 12 all over s square minus s plus 2.
So you have 3 over s
Yes.
plus
12 all over s square minus s plus 2.
Okay, let's verify this real quick. So using the same formulas, we have s squared x of s minus 4s plus 3 s x of s minus 12 plus 2 capital X of s is equal to 3 over s. What Rahman is saying is 3 over s plus 4s plus 12 over s squared plus 3s plus 2. Okay. Abdurrahman's answer is actually correct. If you just move things around, you have that for x of s. And then, actually, there is an additional step. So we said x of s is 3 over s plus 4s plus 4s plus 12 over s squared plus 3s plus 2. This kind of fraction is not the kind, this is correct, but it's not the kind of fraction we want because I have division over s here. I want a polynomial over a polynomial. Later on when we discuss the inverse Laplace transform, you will see that it is easier to deal with that. So this is, you just multiply by s to the numerator and denominator by s. And you have the following. You will have 4s squared plus 12s plus 3 over s cubed plus 3s squared plus 2s. And then with inverse Laplace transform, which we will discuss later, you'll be able to see how to solve this. And from that, after I apply the inverse Laplace transform, I can get x of t, which is the solution to the differential equation. Okay. We have another property, which is the Laplace transform of integrals. This is 1 over s multiplied by capital F of s. Remember, for the derivatives, you're multiplying by s. So for integrals, it corresponds to division by s. So how about this? I will give you a small exercise, and I want you to use the Laplace transform properties in order to find it. I will give you some hints, okay? So here is the following hint. We have multiplication by exponent, right? So the Laplace transform of e to the power of minus at, some function f. This is a shift in the frequency domain. This is hint number 1. Hint number 2 is the Laplace transform of the sine function. Laplace of sine omega t is what? It is omega over s squared plus omega squared. This is hint number 2. So this is hint number 1. This is hint number 2. This is hint number 3. Now, I want you to grab a piece of paper and use these 3 properties. So now I gave you the Laplace transform of the sign, along with these properties, in order to find the Laplace transform of this integral. Do you think 3 minutes are enough? Okay. You have 3 minutes to solve this, right? Please start now. Shabab, how is the exercise? Yes, Yasser.
Doctor, in the first step, we need to use equation 1 and then equation 2, then we will apply equation 3 for all of them.
You can do that, yes. You can do that. I would use equation 2, and then for equation 1, you just shift the variable s by a. Here it's by 2. Then when you apply equation 3, you divide everything by s to capture the integral. So for equation 2, is that clear? So what is the Laplace transform of sine t? So if I have, or sine z, whatever, it's t actually, because we have it, because we have multiple variables, we're using z, so not to mix it up with t. But what is, so we have sine omega t. So Laplace transform is omega over s squared plus omega squared. Here we only have z, so I can multiply it by omega, and divide by omega. With that, we have the following. We have omega over, wait, this is a little bit tricky. Let me, yeah, there should be some omega here, omega z. So the Laplace transform of this guy is omega over s squared plus omega squared. Now we have multiplication by an exponent, so its Laplace transform is actually omega over s plus 2 all squared plus omega squared. We also have the integral, so the result is simply 1 over s multiplied by omega over s plus 2 squared plus omega squared. So this is the Laplace transform of this integral with this function. So basically, instead of using the integration and using the definition, which can get a lot complicated very fast, we can immediately apply these properties to make it easier and then find the Laplace transform of the corresponding function of interest. Any questions? So to answer the question I just heard is that basically you apply 2 to see the Laplace transform of the sign, and then you can shift it and integrate it. So using the properties, you can just manipulate that expression to capture the multiplication by exponents and then to capture the effect of the integral. So this is the result. In the second step, yes, because A is simply 2. So this is a shift by A. In this example, A is equal to 2. It is a specified number. It was not specified when we call it A. Yes, Mazen.
Doctor, do we have to start in the same order, 2, then 1, then 3?
It's up to you. The answer is only one answer in the end. So you analyze it whatever way you analyze it. So you can. So what would you do? What is the alternative that you have in mind?
I did it from started from 3, and then went to 1, but then 2.
You started from 3,
Yes,
and then
applied 1,
okay.
and
So,
then 2.
so you got 1 over s fs plus 2, something
Yes.
like that. And then you computed via 2 what is the Laplace, what is the corresponding, what is that f for the sign? Yeah, that's fine. That's okay. Yeah, as long as you get the correct answer with a meaningful derivation, that's okay. In the end, it's only one answer.
Okay.
So we have another property. If I have a delay in the function by d, then the Laplace transform of that delayed version is the Laplace transform of the original one multiplied by the exponent. So a delay in the time domain corresponds to multiplication by an exponent in the frequency domain. There is a reason why we also multiply by ut minus d, the shifted unit step. This is just to make sure that we only shift this function so that we set everything else to be 0 in other places, so that you also take the 0 with you for the values that are not that are actually 0. Otherwise, you might, if you don't multiply by 2, you might you might get something like this. And you don't want this part. Okay? This is just to make sure that you get the value of the function exactly shifted. So here's an example. If g of t is simply a shifted version of f of t minus 2, then g of s is just f of s multiplied by e to the power of minus 2s. Why? Because a time delay, a shift here corresponds to multiplication by exponent. And notice here we have s here, we do not have t, because we're working in the frequency domain after the transform. Remember this example? Let me remind you of it. When we did this example last week, okay, we figured that it has to be something that we solve by integration by parts. Now, if we go back to the same example, after learning the properties, so here a was 0.5. After learning the properties, instead of doing this by integration by parts, okay, we can split this function into the summation of 3 easy functions to find the Laplace transform of. For example, we know the Laplace transform of AT, right? It is a ramp multiplied by A. You here just to make sure that everything is 0 when t is negative. So this is A over S squared. We know the Laplace transform of the shifted version of it, t minus L. It is 1 over A over S squared multiplied by the exponent using the property we just discussed. We also know the Laplace transform of u, that being shifted. It is AL, I mean we have L here too, multiplied by 1 over S e to the power of minus LS. Okay? Now, what does that mean? If I plot it, it means the following. Basically, this function can be split into the summation of 3 functions. Okay? What are these 3 functions? So this guy is equal to the following. It's equal to this guy with slope A minus this guy. So here at time L, we have another slope to minus A to cancel the effect of that. And then we also need to subtract a unit step at A, at magnitude A. If we do that, you have the following. We need to, sorry, just we need to subtract this guy, because if I cancel this part with this part, we will have positive A here, and we don't want it, so we need to subtract that too in order to have that shifted unit still. So here is the example again. So we have this part minus this shifted part, so it is actually this guy, minus AL, and we get the following function. Was this clear? Okay, good. So let me give you an example. I will go back to the same example that we did by parts, and now I want you to solve it on your own. I'll give you 3 to 5 minutes. I'll give you 5 minutes, and after 2 minutes, I will have some questions. You guys got it? Yes, Mazen.
Yes, you got.
Yes, we got it.
Good. Excellent. Excellent. So we have 0. Oh, wait, Faisal, you're saying 0.5 t over s squared. You're mixing t with s. You cannot do that. You are finding the Laplace transform. So it must be a function of s only. If you have s and t showing up in the same equation, million% sure that there is something wrong in that equation. Okay? So it is simply this guy, but with a being equal to 0.5. So it's 0.5 over s squared. Let me go here. So we will get 0.5. No, actually a is 1, L is 2. So we'll get 1 over s squared. Tell me, what did you get? 1 over s squared, yes. Yes, Abdul Wahab.
I get 1 over s square
Uh-huh.
times 0.5 times minus 2s power minus 2s. Oh, sorry, e to power minus 2s.
Okay. And then
Minus e to power minus 2s
minus e to power minus 2s.
plus 1.
This one?
Yeah, but 0.5 times all, I take 0.5 common factor.
Okay. We can do that. 0.5 is a common factor. So you have 3 terms, right?
Yes.
So what is this plus 1 coming from?
It was 0.5, and when I take it, I make it 1.
Okay, so it was plus 0.5.
Yeah. I take
You don't,
0.5
okay.
from
You don't have a division by s or anything?
division by s. No.
Okay. So again, what is this guy? It is a ramp, right? Minus a shifted ramp minus a shifted step, right? The ramp, what is the Laplace transform of the ramp? This specific ramp, the Laplace transform of it is 0.5 over s squared. This shifted ramp, the Laplace transform of it is 0.5 over s squared e to the power of minus 2s, because I'm shifting it. Now this shifted step is the Laplace transform of it is what? You have 0.5 over s e to the power of minus 2s. Is it clear?
Yes.
Any questions?
Sorry, Dick, but can you repeat it?
Okay, so you agree that we need to we can split this function into summation of 3 functions, right? Do you agree
Yes.
with? So we have this is so if I this is equal to, let me do it again. This function, straight line. Oh, it's bad drawing. Just 1 second. straight line RAM, right, minus, I can have a shifted RAM just to offset this guy, so it stops growing after you move 2 time units, right? If I have this guy minus this guy, then the result will be something like this. You will have a step here, right? Because the slopes will cancel, so you'll have a constant, and you're stuck there. So we want to remove it 2 after 2. So you can just subtract this guy, the shifted step, and the result will be the original function, right? So if I can find the Laplace transform of every element, every function here, every line here, then I can take the Laplace transform of this guy minus this guy minus this guy. It's equal to the Laplace transform that we're looking for. And in this case, the first one, it has the Laplace transform being 0.5 over s squared. The second one is 0.5 over s squared e to the power of minus s. The third one is 0.5 over s e to the power of minus 2s. Actually, there is no 0.5 here. It's just, yeah, just this guy. Okay. Any questions? You guys sure this is an important example? So if you have a question about it, please ask now. Okay. So we use the Laplace transform properties and we find it. The other alternative is to do this by integration by parts if you use the definition. So in the exams, sometimes I will ask you to use properties. Sometimes I'll ask you to use the definition. Sometimes I'll keep it open for you so you choose whatever you want to choose. So it's really up to you. Okay? So I think I'll stop right now.